More pointer examples. This time, well, we're going to use a pointer, actually the dereferenced pointer, so the thing that the pointer is pointing to do arithmetic operations, and use a pointer with one-dimensional arrays. So that's what we're going to cover. We will hold off using pointers in function arguments for next week. So here's my new little simple example. So declare number of objects equals 10. It's just an integer. I just named it number of objects. And then I declare a pointer to the address of number of objects. So pointer, PTR, is going to contain an address, and it's the address to number of objects. So then I'll just print number of objects, but the way I've printed it now is by pointing to it. So this means basically the contents of what I'm pointing to are going to be printed. So let's show that, make sure that that works. There we go. And if I compile it, oops, wrong example, sorry. Save it first. Save, okay, run it again. And as we expect, number of objects is 10. So re-emphasizing what my pointer is doing, this pointer is this is pointing to what's stored at the address that is identified by number of objects. So, and then when I print point literally to, this is called dereferencing the pointer, so I'm outputting literally what the pointer address is, the address held in the pointer variable contains, which is the number 10. Now I can do arithmetic operations on that because this is pointing to an integer at this point. It's pointing to the number 10 that's stored in number of objects. So if I wanted, I could add to it. I could do an arithmetic operation because this is the value that's stored. So save that just to show that that works. Recompile. And yes, indeed, number of objects is now 17. So that was a simple example, I know, but it's pointing out the difference between just declaring something with an identifier and declaring a pointer that holds the address of something that it's pointing to. Okay, now let's look at another example, pointers with arrays. So I declared an array called X with 6 doubles in it, so it's an array of doubles. And then I point to it, so I create a pointer that points to the address of the first element in this array. So X element 0, I'm pointing to the address of where 1.1 is located. And so then let's look at some examples because it gives yet another look at how pointers are functioning. So the first thing I'm going to do is print the value that I'm pointing, the value of pointer. So pointer is an address at pointer is the address of this first element right here, but I'm dereferencing it when I put the asterisk in front. So when I dereference it, I'm not getting the address anymore. I expect to get the 1.1 out. But just to prove that point, I'm also going to say what is the value of pointer. So pointer itself should be an address. So this should put out an address. And technically I should make this format specifier be a P, but then it will put the addresses out in hexadecimal, and not everybody can count up in hexadecimal, skipping values, so I'm going to go ahead and put it out as an unsigned int so that we can look at what's happening a little bit better. So then my next printf statement, I'm saying to print out the value that I'm pointing to. So I should be getting this value, the value that I'm pointing, oops, that's the value that I'm pointing to plus 1. And let's look at, and then this is an address plus 1. And I do have a note here that double values are 8 bytes long. takes 8 bytes to store one of these double values. And then I'll do it for 2 also. And in one case I'm pointing to an actual value. In the other case I'm using the address down here. So let's see what happens. Compile it and oops, run it. So the first line, let me make this so you can look at both together. Yeah, that'll work. So at first I output what I'm pointing to. So it's set up to be pointing to the initial address is the address of the first element. Now I dereference it and I get that first element. So indeed that's what I put out. This second line says put out the value of pointer, which is an address. So this is the address right here, not in hexadecimal, but in something that's more that we can read better. But I put out the address of where 1.1 is located. This next line of code right here, I put out what's at being pointed to the address of pointer plus 1. So I'm adding 1 to the address that's stored at pointer, and I'm taking the value that's stored there. And let's see, is that what happens? Yes, I have, so here it is, the dereferenced value of the pointer plus 1. But an interesting thing happens here. I'm getting the next thing, the next element out of this array, so I'm pointing to the next element. But this guy here took 8 bytes to store. So my address should be jumping up by 8 right there. And let's see if that's what happens. And indeed that's what happens. This is where 1.1 is stored. And 8 bytes later, this is a number 8 higher, this is where 2.2 is stored. So I do it for the next one too. I say let's add 2 to the let's look at what the pointer plus 2 contains. So I have a dereferencer right there. Pointer is an address. I add 2 to the address, but these are all doubles. That means I have to add 16 to the initial starting address and look at what's there. So this is at an address. This is 8 bytes later. This value 3.3 is 16 bytes later. Let's check. Is that what happens? So this is what I get for the initial address plus 2. These are the contents, which is true. That is the third address. And the address literally is 16 bytes higher than the starting address was. Okay, I added 2 more lines to this program. This line, I'm printing the size of the array. That answer should be in bytes. There are 1, 2, 3, 4, 5, 6 elements here. And then I'm printing the size of pointer. So pointer PTR is an address. So this may vary between you and me. I have a 64-bit machine that's 8 times 8 or 8 bytes long, 64 bits. If you have a 32-bit machine, then your size of pointer will vary. So I run that to see the results, and I get the size of the array is 48. Why is the array size 48? Because there are 6 elements in it, and each element takes 8 bytes to store. I said 4, I think, earlier. Each byte takes 8 bytes to store, so 6 times 8 is 48 bytes. This is the size of pointer. Pointer is an address. I have a 64-bit machine, so 64 bits divided by 8 bits per byte means I need 8 bytes to store an address, and sure enough, my pointer is 8 bytes in size, because size of gives you number of bytes. Okay, so the last thing I'm going to talk about your homework assignment for this week, which is it's a little bit different. So this is the homework problem's description that I'm going to upload on Laulima here in a few minutes. This is in Word 2013, so I'm not sure everybody can open it, so I'll also submit it as a PDF. But if you can open it, you're welcome to use this document. So let me explain. So it has two parts. In this first part, you are going to have to submit a document to me with either handwritten answers or typed in answers. So you're going to upload a document to me. You can put your answers in this document and submit it if you want. So there's two problems. One is the part where you have to make some observations and have some answers, which is problem number one, and problem number two is a programming problem as typical. So in problem number one, which is in this document, I basically give you the code. Scroll down. So I give you the code, and you're going to type it into your machine and compile it with the -G option so you can run the debugger. So I give you the code. It looks similar to the one I just did in the video, except instead of doubles, I'm doing it with integers. Then after that, you're going to ask questions. You're going to run the GDB debugger yourself, and you're going to answer questions like, where does this program reside in memory? And since everybody's machine is different, the answers can be a little bit different, but the answers that you give should be, when I'm grading it, consistent. So for example, the first question says, using GDB, find out the address in hexadecimal where your source code resides in memory. Set a breakpoint here. And so you're going to tell me where your source code resides in memory. One thing I guess I would appreciate, which will be at the end of the document, is telling me information about what your computer is that you're using. So tell me if you have a 64-bit machine or a 32-bit machine, or you're running on a Mac, or you're running on a Windows, because I'm interested in seeing how these results vary. You're going to disassemble your code with GDB and just observe it. I disassembled mine and I highlighted where I could see 1, 2, 3, 4, the array values in the source code. You could find them in the source code in the hexadecimal. So it's just an example. So finish looking at the disassembly. It's just informative, and then you'll start running the program step by step. So you'll type run and then execute to execute each run, and then next to execute each line, one line at a time. And then as you're executing your code, you're going to find out what address does the array start at, and then you're going to answer a bunch of questions pertaining to values in the array, pointers, and things that the pointers are pointing to. So and then answer this question. While you're in GDB, issue this command and tell me what the contents are. So you're going to have to think about what the argument is, what address goes with this examine command to tell me what the contents of the pointer are. Then I'll have you go ahead and look at the reference site for GDB and tell me more, decipher what this command means. And then you'll answer a few more questions, how many bytes are used for this and that. And then you're going to fill out this addressing table, which will show addresses of every element in the array and addresses that the pointer is storing. So you'll fill that out. The second part of this homework problem, or this homework set, is to write a program. If you've read your textbook, you will have no problems with this program, so make sure you read your textbook on this problem, and then you'll submit this programming assignment on Laulima as usual.